So in our previous class, we managed to look into the introduction where I listed the formulas which are important as you are to consider the Swinburne's test, which is used as a test for large machines, which are shunt or compound machines. We talked about the energy flow, how this part is used, the indirect method. So make sure that you do go through that part. All right. If you are not on membership, make sure that you join the membership so that you do not miss any of the classes that we are going to be having for our N6 studies. All right. So anyways, guys, we are not going to waste much time. We had formulas. These are the formulas that you're going to actually have in calculation of efficiency. As we have this method on its own, Swinburne's test, which is the indirect method, the summation of losses. I said from the word summation of losses, adding the losses together. You're supposed to combine all the given losses. So on this question, guys, we were given, it's a direct question that we are going to consider. On this question, we have a shunt wound motor. Okay. It's a shunt wound motor. Running light. Running light. This point. It is running light at 750 revs per minute, takes this and that. I explained about these terms. When the machine is running light, it means you are at no load. Those are no load conditions. No load conditions. So at those conditions, you're given the current, this and that. Then later on, they're saying with a logged armature, this part of the armature, there's a statement about the logged armature. So you're going to have information to obtain the currents, maybe the resistance, depending with what you're going to have there from that logged part of the armature. Then after that, the question is, okay, let's move on. Calculate A, the efficiency of the motor when it draws 50 amps. Guys, is this motor drawing 3,5, 3,6 amps? No. It is now drawing 50 amps. Which condition is that one now? Because before it was drawing 3,6 amps. We are now at full load. They are simply saying calculate the efficiency of the motor at full load. That is what we have there. So that is why I was explaining the importance of these diagrams and the formulas that you need at no load and at full load. All right. I don't know what happened. The one at full load, I think it's down there because I remember that I wrote a lot of things, but just make sure you go through that part. But I'm going to explain, guys, on this question. Do not worry in case that you missed our class. All right. So you're going to need those two conditions at no load and at full load. Because the first part, the information there, running light, that the machine is running light, the machine is running light, it means we are at what? At no load. So that is, we are going to need two conditions. So that is our solutions. All right, let's just have our diagrams first. Solution. All right, so for those guys who feel like we spend a lot of time explaining, there is something in that explanation that is important. If you figure it out, then it's important. If not, then maybe somehow you figure it out one day. All right, so no problem. We're gonna have the no load condition. Okay, so at no load, this is a shunt wound motor. So remember, shunt, you're gonna have the shunt field. that is the shunt field windings to the armature. All right, so these are your basic diagrams, guys. I'm just gonna quickly have this part, and also for the full load, all right, gonna consider the full load on another part, and at full load, still the same because we are dealing with the shunt wound motor. All right, so that's it here. All right, to the armature. Okay, so that is it, guys. Okay, so let's figure out the first part. What are we given? At no load, when running light, the speed is given as 750 revs per minute. So we've got the speed 750 revs per minute. Takes 3.6 amps. This is the load current. So at no load, you can use the subscript 1. All right. And at full load, you use the subscript 2. Okay. So meaning to say the current that you are given, which is the load current. Remember, the motor, it takes in the current. So this is the no load, like the load current that we have, but at what? At no load. So you're just going to use 1. Okay. So this is equal to 3.6 amps from 500 volt supply. So the voltage is 500. So V is equal to 500. All right, let me just remove this. That's 500 volts. So if you had to consider, remember when I talked about the speed control, you had such a condition of no load and full load. The terminal voltage is not going to change. So this one is not going to change. We are going to have our terminal voltage as what? As 500 volts. But definitely, the load current here is going to change at full load. We are going to have that is the condition why we consider to say there is a full load, because of this current that we are given, a different current to what we had before. So that is the current that we have at full load. The load current at what? At full load. It's just going to use the subscript 2, which is what? 50 amps. Okay. So the resistance, the field resistance is 250. The field on this condition, our field is what? Our field is 250 ohms. But my question is it going to change here on the full load? No, the field is not affected. So the field will remain as it is. That is 250 ohms. Okay, so as we do understand, this current as it is enters, it distributes another current in the field, another current to the armature, because the motor, it takes in the current. So where we are going to have our output, this and that. Okay, so when a logged armature, 24 volts is required to pass 48 amperes through the armature. These conditions for the logged armature can help us to find the resistance of the armature circuit from these conditions when logged, from these logged conditions, from the logged armature. So we have voltage, we have current. So it means resistance can be calculated. Remember, guys, from your generated EMF, E is equal, this is the back EMF actually, V minus armature current times the resistance of the armature circuit. You want this one. So you're going to make this the subject. We take this to the other side. It becomes a positive armature current, resistance of armature circuit. It's V minus E. Then you divide by what? By the armature current, because you're given that current there. So it simply means the resistance for the armature circuit, which is that the resistance of the armature circuit, just armature, guys, because there is nothing that we have there. We are given for these logged conditions, the voltage is there. V is what? 24. So that's 24 minus E, the generated EMF. But remember, this is at no load. So E is equal to what? E is equal to 0. So there's nothing there. So E will be 0 over what? Armature current passing through the armature. 48 amps is passing through. So that was going to give us the resistance of the armature circuit, 0.5 ohms. So in this case, guys, we are not going to have adjustments like what we had previously, where we are having additional resistors, this and that. No, it's just the armature there. So this will be just the resistance of the armature. So meaning to say, from these calculations, we have the resistance of the armature, 0.5 ohms, and also this side, resistance of the armature, 0.5 ohms. It will be the same. Remember, this does not change. It is not affected. So that is it, guys. The output there, which is the mechanical. All right. So that is it. That is it. From the diagrams, this is what we have, and the information. Okay. From this information, guys, that is what we have. All right, so let us just try to fill in before we consider the question of calculating the efficiency. If there is anything that we can fill into these diagrams, let us just try to fill in the currents, this and that. Remember, the part of the field is not affected, and we can calculate the current for the field. In this case, the field current when having voltage and resistance, just gonna divide. So it is the same, guys, for the first one and for the second one. As you can see, there's nothing that is affected. There's no additional resistor there. So V over RF for the field, that's 500. I'm not answering the question, guys. I'm just trying to fill in my diagram. So this was going to give us 2 amps. Okay. So meaning to say here we've got 2 amps, the same as this part of the field, 2 amps. Remember, when you are having the load current and the field, you can calculate this part of the armature. All right, so you can calculate this part of the armature current for the part of the no load. Okay, so what is the relationship from your Kirchhoff's? This is giving these two. So we are going to simply have the difference. So armature current 1 is simply load current 1 minus what? Minus IF. The difference, guys, your Kirchhoff's law, 3.6 minus 2, which is what? 1.6. So that's 1.6 amps. Your Kirchhoff's laws, again, to find here, as you can see, is the same thing. So meaning to say the armature current here at full load can be determined 50 minus 2, which is 48 amperes. So just write that. All right, so this is what we have. We've managed to fill in our diagram. And remember, I said at no load, the output power will be equal to what? Will be equal to 0, which is not the same, here. The output cannot be equal to 0 when there is a certain load. So the question was to calculate the efficiency at full load. The efficiency. All right. This is a motor that we are having, and I said from our formulas, the efficiencies can be calculated. If you are working with the motor, remember the introduction, guys, of a motor, guys, output over input. And because the output is mechanical, it is difficult. It is actually, we cannot calculate that unless we have a method. So we are supposed to write the output in terms of this input. So it will be input minus what? Losses, which ended up to this part. That formula, guys, it's enough for us to obtain the efficiency. Okay, let me have our formula. So like I said, from our presentation, we simply said, so this will be part A. So the efficiency of the motor, output over input, you substitute those substitutions that you make, guys, in place of the input, in place of the output, which is what? Input minus what? Minus the losses, everything over the input. Just for the sake of revision, you are going to divide by the input, both, then you end up with 1 minus losses over the input, where the input is the one that you consider at full load. So it's voltage times the load current at full load, So use this current at full load. So this is voltage times current at full load. That is at the given current. Remember, they said at 50 amps, that is at full load, at that current that you're given. So that is what you're going to have in this case. And these losses, you remember, these are just the 3 losses that we mentioned before. So we just need those losses, just like that. So guys, do not even worry about this type of a question to say this and that. The formula for efficiency, for finding efficiency, does not change on a motor, on a generator. Just adjustments to those formulas. So meaning to say, let's find the losses, guys. We can find our, this input is direct because voltage is there and also the current is there. So at least let us work with what? With the losses. It can help us because we need all these losses, the 3 losses that we mentioned. So the first one, let's consider the part of the shunt field copper loss, part of the shunt field copper loss. And also on the losses that we are having, the shunt is the same. It is the same thing that is happening. The shunt of this part and the shunt of this part, remember, that part of the shunt, guys, is not affected. There is no additional resistor there. Okay? So that's, we're going to have the shunt field copper loss. Shunt field copper loss. I'm just going to write in short. Remember, those ones, we simply need voltage times what? The current in the field. If you want to use, because their advantage, there's resistance also in the field. So you can also use I squared times R. Okay. You can also use I squared times R, meaning to say, you can also use this formula. It's fine. All right. Still, you're going to obtain the same answers because the current is there. The field resistance is also there. Or you can simply use terminal voltage times the current in the field, which is 500 times 2. So 500 times 2, this was going to give us 1000 watts, which is the shunt field copper loss. Okay. We need to determine the copper loss, the armature copper loss. And those ones are at full load. So meaning to say we are going to need a lot of things. We also need from these losses that we mentioned, we are also going to need the friction, that part of ion, friction and windage losses. But I mentioned that these losses cannot be determined direct. So what you do is that you refer back to the formula. Remember from your energy flow part that you have this formula. Ion, friction, and windage losses are there. So we can simply find them by making the subject. Remember, I explained here that this formula can be manipulated, and we ended up with this formula from the no load condition. All right, let me bring it down here. From the no load conditions, this is what you're going to have at the end to obtain what? The ion, friction, and windage losses. But the output at no load, remember, it's 0. So you can just ignore that one. Or just have your formula, guys. It's in your hands. It's in your hands. So we need to make that the subject. If you do not understand making this the subject, guys, substitute direct here into this formula. If you know this formula here, because that formula is direct, okay? It's in your hands. All right. So let's move on to number 2. So we are going to need C, which is the ion, friction, and windage losses. Okay. So how can we obtain this? Like I said, the formula for the for considering that we are dealing with the motor, we said the input at no load is equal to the output at no load plus the losses, which is the combination of all the 3 losses. Okay. Which 3 losses are we talking about? Let us substitute so that we can be together here. Remember, this is your formula. So we are going to have our losses, the shunt field. All right. So we are going to have the shunt field copper loss plus the armature, which is the armature current, the armature copper loss actually that we are going to have, which is at no load. So at no load, I'm just going to use 1 there times the resistance of the armature circuit. Then also we have C, which is the ion, friction, and windage losses. Remember, this is what you want to calculate. And you can make it the subject like this. Or you can just substitute. Guys, substitute these values. We have the input, everything. Just substitute these values. All right. We having the input at no load. All right. We never calculated this. So we can calculate the input at no load, guys, because we have this voltage and what? Current. So that one, I'm just going to substitute voltage times current. So this one is voltage times the current at no load. So that's load current, just going to use 1. Remember, at no load, the output is 0. So just a matter of substituting, guys. All right. So let us substitute voltage times current. Remember, our voltage is 500. At no load, the current is 3,6, which is the load current that we are having there. All right. We are at no load, remember? So let's substitute. We calculated the shunt field copper loss, remember? So this is equal to, that's a 0 there. Output, it's a 0. So there's nothing, just a 0 there. Plus what? The shunt field copper loss. We calculated this shunt field copper loss. We obtained 1,000. Remember, this is the one that we calculated. All right. Then we have got this part, all right, which is representing our armature copper loss. Are we having this armature copper loss at no load? Have we calculated this? So definitely we didn't. So we need this one. All right. So let's calculate our armature copper loss, guys, at no load. Just I'm just gonna put it here just for the sake of calculation, guys. All right. So the armature copper loss at no load, armature copper loss at no load. So remember, this is the one that is given by this formula, which is armature current at no load resistance of the armature circuit. So the armature current, we calculated this. Remember, we have it 1,6. We calculated this. So that's 1,6 squared. The resistance of the armature circuit, remember, we calculated from that part that we're given, the logged part of armature, what? And we obtained 0,5. So that's it. This was going to give us 1,28 watts, which is at what? At no load. At no load. At no load. We have that part of the armature copper loss. So this one, we calculated this. We got 1,28. So we can calculate the C. Ion, friction, and windage losses. Just like that. So formulas, guys, do not be afraid of these formulas. They just want you to have confusion. How writing this and that. Still one and the same thing, the way that you used to have these formulas. So just combine. So 500 times 3,6 was going to give us 1,800, which is equal to 1,000, whatever that you're going to have here, guys. Just subtract it this side. So you're going to subtract the 1,000, subtract the 1,28, so that you remain with C. So that's it. So the difference of these was going to give us 798,72. Okay, so those are your ion friction windage losses. All right, so that is, we have these ones, guys. So with these, we are left with remember, we need all the three losses. We used a condition. I do not want you to have a confusion on this part where I was saying we are calculating the amateur copper loss. It's very true. It was the amateur copper loss at what? At no load. But in our calculations of this efficiency is needed at full load, at this current that's at full load. So meaning to say, even the amateur copper loss, it is supposed to be calculated from the amateur current, which is at full load. So you must be very, very careful, because you might be saying, on this calculation, when we are calculating the ion friction and windage losses, there's a part where we calculated the amateur copper loss. It's very true, but it was at what? At no load, this one. It was at no load. Now we need to calculate at full load. That's another loss, the third loss. Remember, we're talking of the three losses. So we are going to calculate the amateur copper loss. Amateur copper loss. All right, that's at what? At full load. So that's how you answer this type of a question. Just like that. You just need to find all the losses, all these three losses that you are given. All right. So like I said, this is at what? At full load. So what is going to be the formula? The formula, guys, is not going to change, like this part of armature current squared times resistance of the armature circuit. It's the same. But at full load, so we are going to use what? Subscript 2. We are going to use that armature current, that is the one we are having at full load. Remember from your diagram here, you calculated this when we were filling in our diagrams from the relationship of load current, field current. It gave us what? 48 amps. So we have that one. The resistance of the armature circuit, we have it, 0.5. So that's it. So that was going to give us armature copper loss at full load. So let's just substitute that one, guys. It's direct. So that is the armature current at full load, 48. So that's 48 squared times the resistance of the armature circuit, which is 0.5. So that was going to give us 1152 watts. That is, we have the armature copper loss at full load. The three losses have been calculated. We are considering all three losses. So the shunt field, you cannot say it full loaded too, because this one is the same. It's just the same, but that part of the shunt is not affected. Then the ion friction and windage losses, you take the conditions, which are the ones that you're given at no load, to determine the value of what? Of C, which is your ion friction and windage losses. Once you have these, guys, efficiency can be calculated. Remember, you're determining the efficiency from what? As a motor. So our efficiency, therefore, from our formula, depending with which part you're going to use. If you are using this one, it's fine. You are going to have 1 minus. So this is 1 minus. It's a fraction there. Minus the 3 losses. So you're supposed to have all the 3 losses here. All right. So let's take our losses. Remember the first one, the shunt field copper loss. We obtained 1,000. So this is going to be 1,000. Plus, we move to another one. Remember, we also calculated the ion friction, this and that here. Our C, we have that one. So just combine those losses together. That's 798.72 plus. You also calculated the armature copper loss at full load, this one, which is 1,152. So we're going to have that one again, just like that. Everything over the word. Remember, here we are relating to the input power. Voltage times the current, the terminal voltage times what? The load current. But this load current is the one that you're taking at what? At full load. So this is load current at what? At full load. We have these values, guys. So the voltage, remember, 500. The current, the load current at full load is what? 50. So that's 500 times 50. Just going to multiply that part, all right? So this is going to be 500 times 50, just like that. So the whole of this part, guys, combined together, all this part, as a percentage, we can calculate the percentage efficiency. So we can say percentage efficiency can be calculated depending on the question. Is it about calculating per unit? Per unit, you ignore this 100%. Okay. So that is it, guys. Make sure you use your calculator properly. This was going to give us 88.1712 and so on, which is 88.197%. So just like that. So this is our shunt field copper loss. Moving on to this part, our ion friction and windage losses. This is our armature copper loss, which is at what? At full load. So it is very, very important that you consider all the 3 losses. All right, let's see another part of our question. Try to figure out how these questions can be given. The other part, they need you to calculate the armature current drawn by the motor when it works at maximum efficiency. When it is working at what? Maximum efficiency. What are the conditions? So remember, guys, here we used the subscript 1 for no load. Full load, we used 2. So at maximum efficiency, we are going to use what? The subscript 3. But what are the conditions that we have for the maximum efficiency? All right. Remember, I also talked about this, guys. Also, just a recap for those who missed our class so that you can see what we listed there. All right. So I'm having this part. Okay. So let's just hope, guys, we're going to win. You know, if these videos are too long, they just tend to be something else. All right. Okay, here is where I listed the maximum efficiency and also even how to calculate it. All right. So if you check here about the maximum efficiency, we talked about this one to say for the maximum efficiency when the variable equals the constant, where we are talking about the variable losses and constant losses being equal, and we ended up with this formula. So using this formula, we can determine the current, guys, at maximum efficiency because that is the one that we need. So let us bring that formula into consideration. All right, so that's part B. Remember, for maximum or at maximum efficiency, maximum efficiency, the variable losses, the variable losses must be equal to the constant losses. Okay. And we ended up with a formula because the variable losses, guys, we know those are the ones that are taken from armature circuit. So you're going to use the armature circuit consideration. Then the constant losses, those are the ones that you're going to combine the part of the shunt and those ion friction and windage losses. So it's going to be V times IF, the shunt field, and also the ion friction and windage losses. Okay, so we need this one. We have everything there. So you can calculate that current. The resistance of the armature circuit is the same, remember? So we just need to substitute. So let's substitute, guys, and see. That's the resistance of the armature circuit. Remember, it's the same 0.5. Nothing has changed. The terminal voltage, that's 500. The field current does not change, guys. The field current is just the same for both conditions, which is 2 amps. So thus we have got voltage times field plus C. Actually, we calculated these, guys. Instead of us writing voltage times this, let us just substitute because we already determined these ones before. Remember here, shunt field, we have got 1000. Our C, 700 and something here, 798, this one. We calculated these ones, guys. So just in case maybe you've forgotten that you've calculated, you can also do recalculate. But these ones, guys, we calculated this was 1000 and the ion friction windage losses was 798.72. So that's it. Add these two, divide by 0.5 because that 0.5 is under a multiplication. So you can divide by this one. So just add those two. Then you divide by 0.5. So it was going to give us 3,597.44 like this. Then determining I3, I mean the armature current 3 is you need the square root because of the square, right? So we are going to introduce the square root. Let's just hope, guys, these networks things are not going to affect us in our calculations. All right, no problem. Let's just hope you're going to win. So introducing the square root both sides, that was going to give us the exact value for the current that we need, which is at maximum what? At maximum efficiency, the armature current at maximum efficiency, which was going to be 59.979 amperes. Okay. That is for maximum efficiency, guys, just like that. So questions can be given in that manner or in that format, depending with what you're given. So guys, here I've got a lot of things that I've written. Let me just try to erase some of these things, some of these. Just gonna need the answer here. Maybe we'll need this one later on. Let me just take this one. But for any other calculation, guys, just gonna recall because as you can see, there are a lot of things on our board here. Anyways, let's see. Then the maximum efficiency. After that, they want you to calculate that maximum efficiency. So all there I listed to say, since we are dealing with the motor, we're gonna have this at maximum efficiency. Everything is just gonna remain as it is. But the current that we are using there is the one that is for maximum. The one that we just, the one that you need from the diagram. Now we have to relate from the diagram to calculate that one. Remember, okay, let me write the formula first. So that is the maximum efficiency. Now we need the efficiency. So we saw that the maximum efficiency can be determined 1 minus the losses. So you're considering all the three losses that you calculated there. Then we're going to have the input, all right, which is the current that you're talking about. The load current is at maximum efficiency. We're going to use the 3. Remember, I said let's use the subscript 3. All right, so that is it. So as a percentage, just going to multiply by 100%. So this is it. If we are to consider properly, we are going to see that we need the 3 losses at maximum efficiency. All right. The 3 losses at maximum efficiency will be needed. Shunt, the part of the shunt field. But the advantage that we are going to have is that for these 3 losses, the shunt, this part of the shunt field, copper loss, and also the iron friction and windage losses. These 2, they will actually remain the same. They are not affected. Okay, this is what I'm trying to say. I want you to see this part. Remember, you had these diagrams. At no load, at full load. Nothing had changed in terms of the diagram, like the presentation, like the additional resistor or what. So the field remained the same. Armature remained the same, only these currents. This is the exact thing that also happened here at maximum efficiency. All right, so I want you to see this. This is the exact thing that you're going to also have if you wanted to represent so that you can see or determine the currents for that diagram. So at maximum efficiency, let's just have this one at maximum efficiency. Okay, so we are going to have just like what we this diagram, our shunt wound motor that we had. Okay, so this part I'm just gonna quickly redraw because it's the same. It's just a repetition. The only part that is gonna change is that the input, the load current is going to change. Just like what we had before, when it was at no load, at full load, this current is changing. So it is the same thing even at this maximum efficiency. It is going to change. So we do not know this load current. Remember, at maximum efficiency, we're just going to use the subscript 3. So we do not know that one. But we know our terminal voltage is not going to change. Our V is still 500 volts. The resistance of the field, 250 ohms. This part of the armature, guys, is not going to change because we have the voltage and resistance, which is the same. So it means also the field current has not changed. It is not affected. The armature current, we are going to have the armature current at this maximum efficiency, which is the one that we calculated. Remember, at maximum efficiency, you are being asked to calculate on B, to calculate the armature current at maximum efficiency, and this is what we got. This current is the one that is affecting now the other current. This current that we are now having is going to affect. It is going to affect. So we have 59 point, that's 59.9, 0.979. So we are going to have that one on our diagram. In case that you don't understand this simplification later on. But knowing, guys, to say it was just the same, there's no need for us to even have this diagram. For this one, there's no need. But anyways, so like I said, we had this one, remember, it was 59.979. So this is going to help you with that. Okay, so I can determine this current. Remember our Kirchhoffs. This current is entering the branch, so it is the sum of these two. So you're simply going to add 59.979 plus 2 to obtain what? To obtain this one, which is our load current there. And that was going to give us 61.979 amperes. This is just an understanding of our DC machines, guys. Nothing much. Nothing much. So what's the purpose? The purpose of determining this, guys, it is because of the losses. Remember, I said these losses, they will just remain the same because the part of the shunt field, if you check here, nothing has changed. Sorry, nothing here on the shunt. So the losses will be the same. Remember, losses, you're talking about the power. So what will be the last one? Armature copper loss is going to be affected. So meaning to say here, there was not, if it was not even, this diagram was not even necessary because this current is not even used because we need the armature current to obtain what? The armature copper loss. Okay, so remember here, the resistance of the armature circuit is the same, 0.5 ohms. So that's the only power that we have. So this diagram is not even necessary for here, guys. Yeah, but just for the sake of revision, I want you to see that so that you see in your revisions. So let's add the third loss because these two are the same. So we are going to need what? The third one, which is the armature copper loss at maximum efficiency. So the max, okay, armature. Let's hope we'll be able to finish our questions, guys. Armature copper loss, that is at maximum efficiency. At maximum efficiency. So as we know, guys, our armature copper loss is from the armature current squared times the resistance of the armature circuit. All right. But in this case, okay, you see this thing, guys. Once it starts, it just affects. Okay, so that's a squared here times the resistance of the armature circuit. Okay, so this is what we are now having here. Like I said, guys, yeah, we're just gonna hope it will end well. So this is where we are. Let us just substitute our values. Armature. This is our armature here at maximum efficiency, and its resistance is also there, which is 0.5. So let us just substitute, guys, and square that one. So it was 59.979 squared times 0.5. So that's it. Multiplying these two, it was going to give us 1,798.74. 0. If you round off to 3 decimal places, it was going to be a 0 there. Okay, which is not important. So this is power. As you're talking of the loss, power that we're having there. So this is it. We needed this loss so that it gives us the third one, because these two are already there. Shunt, this one did not change. So this is the third loss that we have. So with these losses that we have, guys, the input power, because all right, so this part here of the load current here is gonna work. Remember the load current here. So it was gonna be necessary, guys, knowing this diagram. Even not knowing this diagram, guys, knowing that the load current is equivalent to the armature plus the field on a motor. There's no need for these diagrams, guys. But just in case, for the revision sake, this one, we are doing it for the revision sake. So I have to make sure that all of us are on the same page. So anyways, let's substitute. So substituting these values, we are going to obtain the maximum efficiency. All right. So that's 1 minus the 3 losses that we calculated before, the shunt, the ion, friction, and windage losses, guys. Those are the ones that we had here. These ones. Shunt here, the shunt field, and also this ion, friction, and so forth. And windage losses, this one. So we're going to add those two. All right. So that's it, guys. So you see, guys, the disadvantage, there's a lot of things here, guys. There's a lot. Okay, no problem. So I just hope, guys, you still recall those values. So we said we have got 1,000. We also have 798, comma, it was 72. Okay, then plus this one of the armature copper loss at maximum efficiency. This is what we got, 1,798,74. Everything over what? The input voltage, the terminal voltage, and the load current for maximum efficiency. So just going to multiply these two, 500, and that load current that we calculated. So that was going to be 500 times 61,979, like this. Okay, so that's it. Having this efficiency can be calculated as a percentage. We can obtain our maximum efficiency. That was the idea of the question. So, guys, you just need to understand your formulas, substitutions, and you see that it's just a repetition throughout. So that's it. Our maximum efficiency was going to give us 88,391%. Conditions of the maximum efficiency led us to calculation of the armature current from part B, then part C, calculation of that maximum efficiency. It's not about just the conditions. They can even ask you to calculate that maximum efficiency at the end. Okay, so you just need to go through more revisions, guys. Let's add as much questions as we can, to be very, very important to add as much questions as we can. Then on another part, let's see. I've erased some of the information which is important that we need here. But anyways, let's see, guys. D, that is the speed of the motor when working at maximum efficiency, the speed. So we are back to those questions, guys, on our speed control. Remember, when you're dealing with speed at no load, at full load, you've got 1 and 2. So this is what is happening. Because they gave us the speed at what? At no load. They gave us the speed at no load. So just like what we had, guys, if you're given no load and full load, you compare the two, the speed control formula. So in this case, we are going to be comparing what? Where you have the speed, meaning say we are going to compare at no load. And the one that we need at maximum, which means that what at maximum where we are using the subscript 3. Now I erased my diagram, but guys, I just hope you still remember how this diagram was. Okay, let us just have this diagram here. So I'm just gonna have my diagram so that we can have this one. So it's just a speed control type of a question. Okay. Just the same part, of your speed control. This is what is happening here. We are going to take the conditions at no load because that's where we have the speed. Then the conditions at maximum efficiency, remember that is where we are using the subscript 3. So meaning to say, as we are writing our currents, this and that, we are going to be using 3 there. So this is what you're going to have. Then you apply that, that part of your speed control, guys, as you had before. So this one, we're not gonna take us time here. We just need that basic view. So here, guys, it's just like, I'm just gonna repeat that diagram the way it was. So I hope you're together because the load current, we calculated this one together. This is at maximum efficiency. So we calculated this. Remember, it was 61.979 amps entering the field. Then the other one going to the armature. And this part of the armature current 3, it was 59. That was 59,979. Okay. Then the field, remember, we're already having this part of the field. It was 2 amps. Resistance of the field, 250, this one. Okay. The voltage, the terminal, 500 volts, this and that. Okay. To the output and the resistance of the armature, which is not changing, which is 0.5 ohms. And definitely the output cannot be 0 here. It is not at no load. At no load, that's where the output is 0. That's the condition that you're simply having. Remember those speed control type of questions that we had before? So meaning to say, comparing these two now, to say I have initial, I have this one at maximum efficiency. We can determine the speed. Remember, we substitute into this formula E1 over E2 in terms of the speed, taking that the flux is proportional to the field current. We can use N1, field current 1 over, okay, this one cannot be 2 because it's now at what? At maximum, where we are using the subscript 3. Remember, at maximum efficiency, we are using this subscript 3. So I'm going to use 3 instead of what? 2. But you used it as E1 over E2. But we are going to use what? 3 because we are at what? Maximum efficiency. The same thing, like I was explaining here, that the current here is just, and the flux, they are proportional. So the speed, you're going to have N3. Then the field current is going to be field current 3. Take note, guys. There is no adjustments in these diagrams in the field. The part of the field is the same. The current that we have in the field there is the same. So this part can even cancel. It's the same. So are we having E1? We do not have. Are we having E3? We do not have. N1, we are given this part of N1, this one. We have it. N3, that is the one that we need the speed at what? The speed when working at maximum efficiency. So we're going to need these guys as we had this topic before. So let's find E1, our E1 from no load. Remember, this is a motor. So consider the back EMF. That is V minus the armature current times the resistance of the armature circuit. But the armature current that we are considering is at no load. So this will be 1, this will be 1. Okay, so let's substitute. That's E1 can be determined. V, we have it. 500 minus the armature current 1, we have it. 1,6. The resistance of the armature circuit does not change, which is 0,5. So that's it. That is it, guys. We're going to obtain E1. That was going to be 499.2 volts as our E1 generated, which is the back EMF. So we have this. We need E3. Okay. From the maximum condition diagram, this diagram, E3 can be determined. So what will be our E3? So E3, just like this one, V minus. So it's going to be armature current times resistance of armature circuit at the maximum efficiency. So meaning to say, we're going to substitute this. E3 is going to be V. That's 500 minus armature current at this condition. That is 59,979 times the resistance of the armature circuit, which is 0,5. So that's it. You're going to obtain E3, which is 490,011 volts. So we have E1, we have E3. Like I said, guys, these currents for the field are the same. So you can even cancel that part of the field. Those currents are the same. So you can even cancel this part here, like it's not there. It's up to you. All right. So let's substitute, guys, into our formula to determine the speed. That is E1 as we calculated our E1, 499.2 over E3. As we calculated E3, it was 470.011. Okay, that's 470.011 like this, which is equal to the speed that we are having initially at no load, 750 over N3, which is the one that we need at maximum efficiency. What is the speed? So as you can see, guys, it's just a matter of change of subject, cross multiplication. You can make the change. You can change the subject first, then you substitute, or you can just cross multiply. Remember, guys, you cross multiplication this here, this one here. So it was going to be the product of these 2499,2 times N3, which is equal to the product of these two 750 and 470.011. So definitely I need to divide by this 499.2. I need to divide here by 499,2. So that was it. We have our N3 speed at maximum efficiency. In revs per minute, since this other speed is given in revs per minute, it means whatever that you are calculating also must be in revs per minute. So that was going to give us N3, which is 706,146, which is in revolutions per minute. So let's do as much revisions as we can. Like I said, it is best that you join the membership. By joining the membership, it means you've got access to any other class that we are going to have, introductions, this and that you're going to be having as we are actually preparing for the exams which are ahead of time. You also need to work more question papers. So maybe you've got a question from a question paper that you need us to attempt or that you need me to work on. That's the purpose now of joining the membership. Because of too much request, guys, we just need to make sure that these things they do balance. So I will advise you guys that you also join the membership. It will be important in terms of revisions, in terms of maybe question wise, okay, question wise, working with more questions. We need to work with more questions. We need to add as much as we can. So let's try by all means to balance, and also that is to balance all the information that is needed before exams. Balance information. Make sure that you have the required information as per your syllabus. What is the syllabus saying? Once you work with the syllabus, you won't go wrong. Work with question papers. You check, okay, they ask these questions this way. And I'm going to attempt these questions this way. We are done. Knowing that, having the idea of the exam. So let's try now to work out question papers where there are challenges. Let's communicate. This is the platform where we can also communicate back so that I can understand what is it that we can work on or that we can add on. Because if you do not communicate, I cannot know, guys, to say this has to be done or this. You're the one who knows, you've been studying. You say, okay, I'm having a challenge here. I'm having a challenge on this question paper. Join membership, ask your questions. So that is it, guys, from Mason African Motives. Till we meet again.